So in this video, I'm gonna introduce memento and impulse. So I know in some textbook they teach work, energy, and power first, and then they talk about memento and impulse. But I decided to do memento and impulse first because it's more connected to Newton's law. And in the next part, I'm gonna talk about energy, work, and power. And I think it's gonna be a really long lesson. So let's go to the learning objective for today. First of all, you need to obtain a basic conceptual understanding of what memento is. So definition, SI unit, and problem that involves memento. And you need to understand the connection between Newton's second law and memento. So for Newton's second law, it states that the net force F is equal to ma, where m is mass and a is acceleration. And for memento, it says memento p is equal to mass times velocity. So see if you can find a connection between those two equations. And you also need to understand that change in memento, so delta p is equal to impulse, so net force times delta t. And then basic diagram and conservation of memento, so collision and memento. Cool. So first of all, let's talk about what is memento. So the most common definition you will see is memento is mass in velocity, right? And that's why memento p is mass times velocity, right? So this is the formula for memento, and memento is a vector quantity with an SI unit with a SI unit of kg times meter per second, right? Because p is equal to mv. So m has a unit of kg and v has a unit of meter per second, and that's why it has a unit of kg times meter per second, right? So this is a basic introduction of what memento is. However, when you learn impulse, you might have a different way of understanding what memento really is. Cool. So memento and Newton's law. So memento is equal to mv, so mass times velocity, and Newton's law states that the net force is equal to mass times acceleration. So how do we connect them? Well, they all have mass, but one of them have velocity and the other one has acceleration. But we also know that change in acceleration is equal to change in velocity divided by time. So m is equal to ma, which is also equal to m times change in velocity over change in time, right? So this is the connection between Newton's second law and memento. So I know mass and velocity might be a little bit abstract to understand, but here it says the net force is also equal to, so here is memento, right? So it's equal to change in memento over change in time. So what we can have is that net force times change in time is equal to change in memento, and this part is equal to impulse, and this part is change in memento. So memento, so let me write this down. So, oops. Oh my. So another way to understand memento is that you can see that as a fact by a force imposed on an object for a certain period of time. So this might be a little bit easier to understand what memento is, because so F net times delta t is equal to delta p, right? So a force imposed on an object for a period of time is equal to momentum. Cool. So we had just talked about impulse. So impulse is F naught times delta t, which is equal to change in momentum, right? So we know net force as a unit of Newton, and time as a unit of second. So impulse also have a unit of Newton times second. So this is impulse, right? So impulse, right? It also is a vector quantity, and is equal to final momentum minus initial momentum, which is equal to change in momentum. Cool. Example 1. A ball is thrown rightwards at a speed of v. After t seconds, the ball collides with a wall and bounces back with a final speed of v with a change in momentum. So you know change in momentum, so delta p is equal to final momentum minus initial momentum. So here is the wall. A ball is initially at a speed of v, and then it bounces back with another speed of v. So you know, because momentum is a vector, so direction matters. So if it initially traveled to the rightward direction, it gotta be a positive v, but after it bounced back, it go to the left direction, so it gotta have a negative sign. So final momentum must be equal to negative mass times velocity, because here velocity has a negative sign, and then here has a positive sign, so minus positive mv, which is equal to negative 2 mv. So this is the answer for this problem. So just be careful with direction and signs. Example 3, a ball of mass 0.25 kg glances at a wall as shown in the diagram. The ball approaches at 50 meters as theta is equal to 30 degrees, and it lifts at 12 meters per second at phi is equal to 20 degrees. The collision lasts for 15 milliseconds. What are the components of the impulse experienced by the ball? So to calculate impulse, you need to calculate change in momentum for each component, so for the horizontal component and for the vertical component. So let me do this here. So here's what I am gonna do. So let's say here is your initial momentum here. So you can separate them into different components. The horizontal component, P at Y, and the horizontal component. And we know this is gonna be equal to mv sine theta. And this is gonna be equal to mv cosine theta, right? And here, let's say this is your final momentum. So pf, same thing, separate them into different components. So pfx, so your final horizontal momentum is gonna be equal to mvf cosine phi, and pfy is gonna be equal to mvf sine c, right? And you just need to calculate change in momentum right now. So let me copy paste this. So let's calculate the horizontal direction first. Another. So change in momentum, so for x direction, change in momentum is equal to impulse. So for x direction is gonna be equal to your final horizontal momentum minus your initial horizontal momentum. So for your final horizontal momentum is pointing to the rightward direction, so gotta have a positive sign. So mvf cosine phi minus your initial horizontal momentum also have a positive sign because it's also pointing to the right direction. And v cosine theta, which is equal to 0.25 times 12 cosine 20 degree minus 0.25 times 15 meter per second cosine 30 degree. And this is equal to negative 0.4285. So this is for your horizontal direction. And now let's calculate for the y direction. So for y direction, so the change in momentum is gotta be equal to your final horizontal momentum minus your initial horizontal momentum. So let's go back to the picture here. So initial momentum gotta have a minus sign because it's pointing downward, and final horizontal momentum gotta have a positive sign because it's pointing upward. So here for final momentum is gonna be equal to VF sine theta minus the initial momentum has a negative sign, so minus v sine theta. So this is equal to 0.25 times 15 times sine 20 plus, so 2 minus 2 negative sign is gonna be a positive sign. Times velocity, so 15 meter per second times sine 13 degree. So this is equal to 2.9011. And the second part is asking us to find the component of average force acting on the ball. So let me copy this answer first. Oops. So here is impulse for a horizontal direction, and here's for vertical direction. And we know force, so average force is equal to change in momentum over change in time. So for x direction, the average force is just gonna be px over delta t. So change in momentum is just equal to your impulse, so is equal to ix over delta t, which is equal to negative 0.4285 over time, so 15 millisecond. You need to do the unit conversion, -3. So millisecond to second, you just multiply by 10 to the -3rd power. So this is equal to negative 28.6 Newton. Right. So this is for your horizontal direction. Now let's calculate for the y direction. It's gonna be equal to your vertical change in momentum, so y direction over delta t. Change in momentum is equal to impulse, and this is equal to 2.9011 over 15 times 10 to the -3rd power. So this is equal to 193.5 Newton. So this is our answer. So this is the right version answer from the PDF in time graph. So you need to understand what quantity is represented by the area under the curve. So area under the curve. Well, let's think about it. So let me note it here. Forces versus time. So I will just draw a random line here. So what does the area here represent? So let's think about it this way. Let's say area. So actually, let me change this picture a little bit. So area will just be equal to force times delta T. This is the area, and this is also impulse, right? And impulse is also change in momentum. So from this picture, you can have intuitive understanding that the area represents impulse, which also represents change in momentum. And this is what force and time graph represent. So it represents impulses and change in momentum. One thing you need to be careful about is that impulse is still a vector, so direction matters. So let's say for this picture here, for this one, area under the curve is y. So let's calculate. Area is equal to, so here is equal to 1.5 times 2 times 4t. And here the area is the same, so let's do this first. So here is 20, and for this one here is equal to 1 times 40, and for here is still equal to 20. So add up all the number. We know the impulse is equal to 20 plus 20 plus 40, so 80, right? Newton per second. So it has a positive sign here, because it has a positive force, right? But for here, for this picture here, this is the delta T, but here we have a negative force here, right? So the momentum for this picture is gonna be negative 18 Newton per second. So just be careful with how the sign changes based on direction or based on the force. And for this picture here, we can know a constant force, right? So force does not change with time. So you also need to understand what those picture is representing, because you might see a problem that describe a situation and they only give you a graph. So here they can say a force is applied on an object in the rightward direction, and then after 4 seconds the force start to decreases until the force is equal to 0, so no force is on the object, and then you also can use those pictures to calculate the mental impulse. So let's do a quick example. Example 1, a 0.5 kilogram ball is dropped from rest above a hard floor. When it reaches the floor, it has a velocity of 4.0 meters per second. The ball then bounces vertically upward. The figure is a graph of velocity against time for the ball. The positive direction for velocity is upward. Find the magnitude of change in momentum during the bounce. So you need to understand the graph first before you're doing this kind of problem. So one thing you need to pay attention is that the positive direction for velocity is upward, meaning that if the ball is going upward, it is having a positive quantity, right? So here, when the ball reaches the floor, it has a negative velocity because it's going upward, but the graph here says use a positive quantity to represent downward direction. So just don't be tricked by this graph here. So when it reaches the floor, it has a speed. Here actually you can think it is speed, but I will still say velocity. So it has a velocity of 4.0 meters per second, but here gotta be a negative quantity, so I will put a minus sign here. And when the ball hit the floor, it bounced back, so it's going upward, so it gotta have a positive quantity. So here actually should be a positive number, and here should be a negative number here. right? So change in momentum is equal to pf minus pi. So pf, final momentum, basically just the momentum when the ball bounced back. So is equal to 0.5 times 2, having a positive quantity because going upward, which is equal to 1. And here is equal to 0.5 times negative 4 because it's going upward, which is equal to negative 2, right? And pf minus pi is equal to 1 minus negative 2, which is equal to 3 Newton second. So the answer is 3. If you take the magnitude, is the absolute value of this quantity, which is still 3. Part B asks us to find the average force exerted on the ball. What's the time of 0.15 seconds? So we know average force is equal to change in momentum over change in time, which is equal to 3 Newton per second over 0.15 seconds. So it's equal to 20 newtons. So this is the answer. So this is the solution from the textbook. Give us a exam tip. Yeah, you can just read the PowerPoint. Conservation of momentum. So conservation of momentum is very important. Basically, what they're saying is this: the total momentum in the system is conserved, meaning is constant. So pi gotta be equal to pf, initial momentum, gotta be equal to final momentum, right? So this is pretty straightforward, but you might see problem involving collision. So there are basically two type of collision. So inelastic and elastic. So collision has elastic collision and inelastic. So elastic collision basically is a two object does not stick together. And for inelastic, objects stick together. So for example, here is object 1, M1, here's object 2, M2. They're traveling with the speed of v1, and then it collapsed. And what happened is object 1 might travel in this way, object 2 might travel in this way. But for inelastic collision, it's gonna be like this, M1, M2 traveling at a speed of v1. So M1 cloud was object 2, and then it becomes something like this. So this is M1, and this is M2. They stick together and traveling at a velocity of vf. For both cases, collision is conserved. Momentum is conserved. So here show you the case. You haven't learned kinetic energy, but it's good to know that for collision, the total momentum is conserved, but kinetic energy is not conserved. So let me write it here. So first, let's talk about elastic collision. Right, so here, this is M1, and this is M2. So M2 is at rest, and M1 is traveling at a speed of v1, so initial velocity. And what happened is they collapse. So here gotta be M1, M2, and it's traveling at a speed of v1 off and v2f. So because momentum is conserved, then pi must be equal to pf, right? So the equation now becomes something like this. So let me write this. Initial momentum is equal to final momentum here. So let me redraw this picture. 2 I actually should erase this 2 here. Right. So how do we calculate initial momentum? So we know initial momentum is equal to P1I plus P2I. So mass 1, mass 2, which is equal to P1F plus P2F. And for 1 is equal to 1 V1I plus 2 V2I plus, is equal to M1 V2F, V1F, plus M2 V2F. So this is the equation you need to know. In our case, we say M2 is initially at rest. So what we can say is that M1 V1, so here gotta be 0, is equal to M1 V1F plus M2 V2F. So having this equation, you can solve different problem. And now I will talk about inelastic collision. So objects stick together, right? So same thing, M1, M2 traveling at a velocity of v1i after collision. So before and after, it becomes something like this. Traveling at speed of vf. So in this case here, M1 and M2 have the same velocity. So we know momentum is conserved, so pi is equal to pf. So here is equal to m1 times v1i plus m2 plus v2i, which is equal to, because stick together, so you can see them as one object, m1 plus m2 times vf. And this is the equation for inelastic collision. And if we say m2 is initially at rest, the equation becomes m1 plus times v1i is equal to m1 plus m2 times vf. Right. So this is momentum of collision. So let's do a simple example here. Example 1, while chasing a armed suspect into and onto a ice rink, a police stable is shot. Fortunately, the stable is wearing bullet-proof vest, which absorbs the bullet. If the muzzle velocity of the bullet is 350 meters per second and its mass is 100 kilogram, find the velocity of the constable and the bullet if her mass is 69.5 kilogram, assuming all motion in the straight line is in a straight line and ignore friction, and also assume the stable is at rest. So at rest meaning have a initial velocity of 0, right? So for this problem, you can use conservation of momentum. So pi is equal to pf, right? So think about the scenario. Let's say this is the police stable, and here is the gun, and here is the bullet, which having an initial velocity of 315 meters per second, and when the velocity is here, the bullet here, the bullet and the police constable can be seen as one object, right? It can be seen as a whole. So PF is equal to police plus bullet times VF, and initial momentum is equal to police times V1I plus bullet times V2I. And here it says the constable is at rest, so here gotta be 0. Right, so we're gonna have bullet times V2I, which is equal to police plus bullet times VF. So VF is gonna be equal to bullet times V2I over police plus bullet. So let me erase this. So VF is gonna be equal to 350 times 100 gram is equal to 0.1 kilogram over 0.1 plus 69.5, which is equal to 0.5 meter per second. So this is your answer. But let's think about it. This is a bullet and having a velocity of 0.5, so it's going this direction. So what we can say is the police goes backward. Oops, sorry. At a speed of 0.5 meter per second, right? So it's going this direction. And this is just the answer from this one. So here is going backward at a velocity of 0.5, so meaning going this direction. So I draw the opposite direction, but it's both going like backward. Example 3, a 3,000 kilogram truck traveling at 50 kilogram per hour strike a stationary 1,000 kilogram car, locating the two vehicles together. So inelastic collision was the final velocity of the two vehicles. So VF is equal to y. So PI is equal to PF. So this is a very straightforward problem. So you just need to calculate initial momentum is truck times VTI plus, let me do step by step, plus car times V car initial times truck plus car times VF. And here is equal to 0 because it's in stationary, so velocity is equal to 0. So VF is gonna be equal to truck. So 3,000 times 50 kilogram per hour over 3,000 plus 1,000. Right, and the answer is 37.5 kilogram per hour, and you can convert it into second. So this is example 2. I don't have example 3. I'm sorry. And this is a reference for this lecture, and I hope you find this lecture helpful. Follow my website for more resource and subscribe my channel if you like it. Put your comments down if you have any suggestion. And thank you guys for watching this video.